Hello, I'm going to go over the c152 Pop Quiz 2, which was given on Thursday in Dr. Daly's class. So the first question asked about, what are the dependencies on the rate constant? And I ask this because oftentimes we're going to ask on the exam about the rate law, about the rate constant. I just want to make sure that everything's clear about what the rate constant depends on. So the rate constant formula, which will be given on the test, is going to look like this, where A is the collision effectiveness, E, delta E or EA, a lot of different places have different values. This is the activation energy and temperature. So the rate of reaction, right, which is the rate of appearance of products, which is the same as the rate of disappearance of reactants, depends on the rate constant and the concentration of reactants in the slowest step. So we spent a lot of time on Unit 5, Module 3, speaking about that. And so K is not concentration dependent since the K is multiplied by the concentrations in the rate law. So K itself is only going to depend on collision effectiveness, activation energy, and temperature. So in this particular question, we expected that only B and C would be chosen. Question 2 has a mechanism. It's a slow-fast, and we ask you to construct the energy diagram. The key in constructing energy diagrams here in the mechanism is identifying that 1, there's 2 steps, and 2, it looks like that both of the products in each step have AA bonds, which we expect to be endothermic based on our analysis from Unit 5, Module 1. That means that we're going to have to pick the diagram, which all of the energy diagrams shown, A through D, are showing a 2-step mechanism. But they're all showing different types of mechanisms in terms of, is there a slow versus fast? Is there an endothermic and exothermic step? So when we look at this, we see that the first step, since it's endothermic and it's slow, has to have a high activation energy. And the intermediate has to be higher in potential energy than the reactants. The second step has to have a low activation energy, and it's also going to be higher in potential energy. So overall, the reaction is endothermic, both steps, and the first step, activation energy, has to be greater than the second step. So we would expect that the answer would be B, that the potential energy would look like this with the reaction progress. The 2-step mechanism, both of them endothermic, with the first step being the slow step. The next is the 3-step mechanism, and in this question we wanted to make sure that all of the different types of questions are presented. So from the slow is the first step again, and that means that we can immediately write the rate law as K times the reactants in the first step, which is CH4, which means that if we double CH4, we'll double the rate. We cut CH4 in half, we'll cut the rate in half. It also means that any other reactant can be doubled or tripled, and there would be no effect on the rate. Let's take a look. That means that A is correct because we would double the CH4, its first order, and we would double the rate. To identify the endothermic and exothermic, we're going to take a pretty standard approach that we did during exam 1, which is that if one particle makes 2, we expect a bond to be broken and delta H should be greater than 0. 2 particles make 1 particle. We expect exothermic as a bond is formed. By using that analysis, we see that step 1 and 2 are endothermic as you go from 1 particle breaking into 2. And then we have step 3, which is 2 particles making 1. We would consider that to be exothermic. The overall reaction, we got to add up all the reactants and all the products on both sides. If we do that, we write all the particles there, and we see that there's some intermediates that cancel out, and we're left with CH4 plus CO2, making 2H2 plus 2CO. AA bonds present in the reactants, just like the previous problem. So we expect an overall endothermic. So we expect that 1 and 2 are endothermic, but step 3 is exothermic. Overall, it's endothermic. And increasing the rate will increase the rate of reaction and the extent, because we will make more products since they're at higher potential energy. By adding more kinetic energy in the system, we will have greater access to the product. So we expect the extent to increase, as the extent is the ratio of products to reactants. Okay. So the next question was based on a Let's Think activity that we did in class. And if you can't read what the text was, we have ozone breaking apart into O2 plus O that had a high activation energy, the slow step. Then the O that's made as an intermediate reacts with another O3 to make 2O2. The overall reaction is 2O3 to 3O2. Slow step in the first one, fast step in the second. So we see that only one particle, only one substance was involved in the first reaction, so the molecularity is unimolecular, first order. And the second reaction, which is the fast step, it was bimolecular, that involved two different particles. The last question asked to identify what would be the concentration versus time of the chemical reaction at low temperatures. So that's just a way to ask you a variety of questions coming from Unit 5, Module 2, which is we need the overall reaction here because we need the overall delta H and the overall delta S to quantify what happens at low temperatures. So we do that, we write out the entire chemical reaction, and we see that the overall reaction is CH4 gas, water gas, two water gas molecules, reacting to make CO2 plus 4H2 gas. Again, we have AA bonds in the products, so we would have an endothermic reaction, and we have 5 particles being made versus 3 in the gas phase. So we would expect delta H to be greater than 0 and delta S greater than 0. Drawing the PEC diagram for that, we would see that, so high potential energy products, then we have the case where directionality is temperature dependent, extent is always temperature dependent. We see that at higher temperatures we should make more products, and the directionality argument is that we're going to go to product favored at high temperatures, and at low temperatures we would be reactant favored, fully reactant favored. We can draw the delta G versus T. That's going to say the same thing, very consistent with it. Reactant favored at low temperatures, product favored at high temperatures. And we're asking about low temperatures, so we need a curve that represents product favored, meaning that there's more reactants than product at equilibrium, which is shown with the flat lines at the end. Okay, so Unit 5, Module 3 has these questions. And if you have any questions regarding this material, please make sure that you visit SI session or come to office hours. Happy to talk to you about it.